Hi, I'm Kyle Hatch. I'm an undergraduate student at Stanford University. I'm in my senior year studying computer science, and I will be presenting our paper, Obstacle Avoidance Using a Monocular Camera, which I completed in the Stanford Intelligent Systems Laboratory with my co-authors John Myrn and Michael Kokendorfer. In this work, we developed an obstacle avoidance system for small UAVs. There are two key characteristics that define our work on this. The first is that the sensor input to our obstacle avoidance system consists of only monocular images from an onboard camera and vehicle odometry measurements. The second is that we developed a hybrid control system that combines deep reinforcement learning and online path planning methods. Our system builds on several areas of prior work. The first is the use of convolutional neural networks for depth estimation. Several prior works have shown that convolutional neural networks, a class of neural networks specialized for images, can be trained to accurately estimate depth from monocular images. The second is the use of deep reinforcement learning for obstacle avoidance. Deep reinforcement learning is a machine learning method in which an agent learns by trial and error to complete a sequential decision-making task. Prior work has used deep reinforcement learning for UAV obstacle avoidance systems. Thirdly, hybrid learning and path planning systems have been developed for UAV control, although not in the context of collision avoidance using a monocular camera. As mentioned previously, one of the key characteristics of our obstacle avoidance system is that it uses monocular camera images as its primary sensor input. So what is the motivation for developing an obstacle avoidance system based on monocular camera images? This primarily has to do with the fact that small UAVs have size, weight, and power consumption constraints that prohibit them from using more specialized sensor equipment such as LiDAR or radar. Small digital cameras, on the other hand, are lightweight, inexpensive, and have low power requirements, making them ideal for use on small UAVs. However, a central challenge to this approach is that monocular camera images do not contain any explicit depth information about the scenes that they capture. Another key characteristic of our obstacle avoidance system is that it uses a hybrid control approach, combining deep reinforcement learning and online path planning methods. To understand the advantages of our hybrid approach, we need to examine the pros and cons of reinforcement learning methods and path planning methods individually. A primary advantage of deep reinforcement learning is that it can be very effective in solving high-dimensional control problems. However, deep RL can be ineffective for solving multi-objective or constrained problems. This is in part because neural network behavior is highly sensitive to the choice of reward function, which serves as the optimization target during training. The task of piloting a UAV to a goal destination while avoiding obstacles is inherently a multi-objective problem. The objective of reaching the goal destination in as little time as possible must be balanced with the objective of minimizing the risk of collision. Tuning the reward function such that the network learns to solve the target task while avoiding failures is difficult, and incorrect parameters can lead to undesirable behavior. On the other hand, path planning algorithms can be very effective at planning flight routes that are subject to safety constraints. However, with map uncertainty, path planners can rely on overly conservative behavior in order to ensure safe operation. This can cause the generated vehicle paths to be much longer than optimal. A hybrid control approach can leverage the advantages offered by both deep reinforcement learning and online path planning methods, while minimizing their disadvantages. Our hybrid system is able to efficiently solve a high-dimensional control problem that is also subject to safety constraints. At the same time, it does not rely on extensively tuning the reinforcement learning reward function, and minimizes the use of overly conservative path planning routes. Our hybrid system is composed of 3 neural networks and a contingency policy. Each of the neural networks performs a distinct task. A convolutional neural network, which we call the depth estimation network, is used to estimate depth maps for monocular camera images. A second neural network, called the policy network, is used to pilot the aircraft during normal flight. A third neural network, called the collision prediction network, estimates the probability that the vehicle will collide with an obstacle within a receding horizon window. If the predicted collision probability exceeds a threshold, control of the aircraft is temporarily given to the online path planning contingency policy. The contingency policy safely pilots the aircraft around the obstacle and then returns control of the aircraft to the policy network. The complete system is outlined in this diagram. The input to the system is a monocular RGB image taken by the camera on board the aircraft. This image is passed to the depth estimation network, which outputs an estimated depth map. The flattened depth map is then concatenated with the aircraft's internal odometry measurements. This is then input to the collision prediction network, which outputs the probability of a collision occurring within the next 10 time steps. In our experiments, our system operated at 10 Hz, so this corresponds to estimating the probability that a collision will occur within the next 1 second of flight time. If the estimated probability of collision is greater than some threshold, for example 0.5, or if h of t minus 1 is true, then the aircraft is piloted by the contingency policy. H of t-1 is simply a variable that indicates that the contingency policy has been activated by the collision prediction network and has not finished piloting the aircraft along the path that it planned. Once the contingency policy has been activated and it finishes piloting the aircraft along the path it planned, then H of t is set to false. If the estimated probability of collision does not exceed the specified threshold and the contingency policy is not in the process of being executed, then the policy network chooses a velocity command for the aircraft to follow. I will explain each of the three networks and how they are trained in greater detail in the following slides. As mentioned before, the depth estimation network is a deep convolutional neural network. It was trained to map monocular RGB images to downscaled 9x16 depth maps. Each cell in the downscaled depth map contains the estimated minimum distance of any obstacle in the receptive field of that cell. An RGB image with corresponding full resolution and downscaled depth maps are shown at the bottom of this slide. The depth estimation network was trained using supervised learning, a machine learning method in which a model is trained to map inputs to outputs using labeled training data. We trained this network on a dataset of simulated images and corresponding depth maps gathered from the aircraft's onboard camera in the Microsoft AirSim simulator. The policy network is a simple, dense, feed-forward neural network. It is trained to map the estimated depth maps concatenated with the aircraft's odometry measurements to a discrete set of velocity commands. The policy network was trained using Rainbow DeepQ learning, a state-of-the-art reinforcement learning algorithm for problems with discrete action spaces. The reward function used for training is shown below. This function rewards the RL agent for moving the aircraft towards its destination, or gives it a negative penalty if the aircraft collides with an obstacle. The collision prediction network is also a simple, dense, feed-forward neural network. As mentioned previously, it was trained to estimate the probability that the aircraft would collide within the next 10 time steps or 1 second of flight time. The collision prediction network was trained using supervised learning on a dataset of estimated depth maps and odometry measurements gathered when the aircraft was piloted by the policy network. We trained and evaluated our system using the Microsoft AirSim simulator. Our system was trained to navigate through an obstacle course that we created in the AirSim neighborhood environment. The UAV's goal was to fly from one end of a street to the other. Cars were placed as obstacles in the street, and the aircraft was constrained to fly at an altitude approximately equal to half the height of the cars. At the beginning of each episode, the lateral position of each car was randomly assigned. Images of this obstacle course are shown below. The depth network, policy network, and collision prediction network were each trained separately. The best performing instance of each of the three networks was then integrated into the complete system, and the performance of the complete system evaluated. We tested both a rules-based expert policy and an online path planner based on the A-star algorithm as the contingency policy. As input to A-star, a 2D obstacle map was generated using the last depth estimate frame. A-star was then executed until a route around the obstacle was found. The rules-based policy is a simple expert policy designed to pilot the aircraft around an obstacle in front of it. These contingency policies worked well for the experiments we conducted. However, the policies can be replaced by any suitable policy or planner. Systems that only used either the RL policy or the expert contingency policy were also tested as baselines for comparison. The hybrid system using the expert contingency policy achieved a completion rate of 94.9%. This is significantly higher than the completion rates achieved by the RL policy alone or the expert contingency policy alone. The hybrid system using the expert contingency policy achieved an average completed episode length of 440.2 time steps. Although this is longer than the average completed episode length achieved by the RL policy alone, it is significantly shorter than the average completed episode length achieved by the expert contingency policy alone. This shows that our hybrid approach is able to balance the objective of quickly reaching its destination with the objective of safely avoiding collisions. The lower performance of the hybrid system using A-star is likely due to noise in the depth estimates generated by the depth estimation network. In contrast, the expert contingency policy relies very little on the depth estimates generated by the depth estimation network. In conclusion, we present an obstacle avoidance system for small UAVs based on a hybrid neural network and path planner controller using monocular images as input. By decomposing the problem of collision avoidance into two modes of operation, our hybrid system leverages the advantages offered by both reinforcement learning and online path planner methods. Using the policy network as the default controller of the aircraft avoids using a highly conservative path planning algorithm when such caution is unnecessary. This enables the hybrid system to pilot the aircraft to its destination more quickly than if the contingency policy were to control the aircraft the entire time. However, in high-risk situations, a conservative contingency policy can pilot the aircraft around nearby obstacles more safely than the learned reinforcement learning policy can. In this way, our system balances the dual objectives of quickly flying to a goal destination and avoiding collisions without requiring extensive tuning of the reinforcement learning reward function. The purpose of this work is to demonstrate that a hybrid approach to collision avoidance for small UAVs can outperform approaches that rely on reinforcement learning or path planning algorithms alone. Future work will explore replacing the contingency policies that we used with more sophisticated path planning algorithms, such as uncertainty-aware Monte Carlo tree search or Hamilton-Jacobi reachability. Thank you.